Welcome to our deep dive into parasitology. Today, we are going to explore one of the most fascinating and dangerous parasites known to science, Leishmania donovani. We will uncover how it outsmarts the human immune system, understand its complex life cycle, and learn the mathematical models epidemiologists use to predict and control its spread. Let us get started. To begin our journey, imagine a clever burglar who does not just break into your house, but actually hides inside the very police cars sent to catch them. This is exactly what Leishmania donovani does in the human body. Instead of running away from our immune system, it deliberately gets swallowed by our immune cells, specifically the macrophages. It then uses these cells as a safe house to multiply and spread throughout the internal organs. This incredible trick makes it a highly successful and deadly invader. Now that we understand its evasion strategy, let us look at its biological forms. Leishmania donovani is a protozoan that exists in two distinct morphological stages to survive its complex life cycle. Inside the gut of the female sandfly, it takes the form of a promastigote. This form has a flagellum, making it motile and perfectly adapted for survival in the insect. However, once injected into a mammalian host, it transforms into an amastigote. This form is round, lacks a flagellum, and is specialized to multiply exclusively inside our immune cells. Because this parasite multiplies inside our immune cells, it leads to a devastating systemic disease. By invading the reticuloendothelial system, specifically the spleen, liver, and bone marrow, it causes massive organ enlargement and severe immune dysfunction. This disease is known as visceral leishmaniasis, or Kala-Azar. It is absolutely critical to study this because it is the second largest parasitic killer in the world, right after malaria. It primarily affects the poorest populations in developing countries, and if left untreated, the mortality rate is nearly 100%. Rapid diagnosis is a literal matter of life and death. To fully grasp how this disease spreads, let us examine this diagram of the parasite's life cycle. On the right side, you can see the sandfly stages. The elongated, flagellated promastigotes multiply in the midgut and move to the mouth parts. When the sandfly bites a human, it injects these promastigotes, crossing over to the human stages on the left. Here, you see the large blue macrophage engulfing the invader. Inside, they transform into round amastigotes, multiply, and eventually burst the cell to infect others. Finally, another sandfly takes a blood meal, ingesting the amastigotes, and the cycle begins all over again. Having seen how the parasite cycles between hosts, we must now ask how public health officials track its impact. To control visceral leishmaniasis, we need to quantify the disease burden in affected communities. Epidemiologists rely on two key metrics. The incidence rate measures the flow of new infections occurring over a specific period. However, because Kala-Azar is a chronic disease that lasts a long time, we also need to measure prevalence, which tells us the total proportion of the population that is currently infected at any given time. Understanding this distinction is vital for allocating medical resources. This need to measure the total disease burden brings us to a fundamental epidemiological formula. Conceptually, if new cases keep flowing in and the disease lasts a long time, the total number of sick people will accumulate. The formula is P equals I times D. Here, P stands for prevalence, which is the total proportion of the population currently infected. I is the incidence rate, representing the number of new cases per person year. Finally, D is the average duration of the disease in years. If either the rate of new infections increases or the disease takes longer to cure, the overall prevalence in the community will physically increase. Before we move on, let us see this formula in action with a concrete example. In a rural village in Bihar, health workers record an incidence rate of 0.05 new cases per person year. The average duration of the infection before treatment is 2 years. We are asked to find the estimated prevalence. We chose the P equals I times D formula because Kala Azar is a chronic, long-lasting infection. We substitute 0.05 for I and 2 for D. Multiplying these gives us 0.10. Physically, this means 10% of the village population is actively suffering from the disease at any given time, indicating a severe outbreak. Now that we have calculated the prevalence and identified a severe outbreak, we must figure out how to stop it. A high prevalence means we need aggressive sandfly control. To do this effectively, epidemiologists measure how intensely the sandflies are transmitting the parasite using a mathematical concept called vectorial capacity. This metric is crucial because it evaluates all the environmental and biological factors that drive an epidemic. It essentially tells us the average number of potentially infective bites that will eventually arise from all the sandflies biting a single infected human on a single day. To quantify this transmission risk, we use the vectorial capacity formula. Conceptually, this equation combines the density, biting habits, and lifespan of the sandfly. C is the vectorial capacity. The variable M is the ratio of sandflies to humans. The variable A is the average number of human bites a sandfly takes per day. We square it because the fly must bite twice to transmit the disease. The term P to the power of N represents the probability that the sandfly survives the parasite's incubation period. Finally, the denominator, negative natural log of P, represents the daily mortality rate of the sandfly. If the sandfly density increases, or if they live longer, the transmission capacity skyrockets. Let us apply this complex formula to a real-world scenario. An entomologist finds 10 sandflies per person, so M equals 10. Each fly bites humans 0.2 times per day, so A equals 0.2. The daily survival rate, P, is 0.8, and the parasite takes 5 days to mature, so N equals 5. We're asked to find the vectorial capacity. Our first step is to calculate the probability of the sandfly surviving the incubation period, which is P to the power of N. We calculate 0.8 to the 5th power, giving us 0.32768. This physically means only about 32.7% of the sandflies live long enough to become infectious. With the survival probability calculated, we can now complete the evaluation. We are given that the daily mortality rate, the negative natural log of 0.8, is 0.223. We substitute our density of 10, our squared biting rate of 0.04, and our survival probability into the numerator. We then divide by the mortality rate. Multiplying the top terms gives 0.131072. Dividing this by 0.223 gives a final vectorial capacity of approximately 0.587. Because this value is less than 1, it physically means the current sandfly population cannot sustain a massive epidemic. We have covered a lot of ground today, so let us summarize our key takeaways. First, we learned that Leishmania donovani is a master of immune evasion, surviving by multiplying inside the very macrophages meant to destroy it. Second, we saw how epidemiologists measure the massive burden of Kala-Azar using the prevalence formula. Finally, we used the vectorial capacity model to understand how sandfly density, biting rates, and survival dictate the risk of an outbreak. By mastering these biological and mathematical concepts, you now understand the tools needed to eradicate this devastating parasite. Great work today.